Hello guys, thank you for watching this lecture. We are learning linear algebra and this is the best time to learn tensors. So in this lecture, we will see the definition and basics of tensors, tensor operations, tensor decomposition, and properties of tensors. What is tensor? A tensor is a mathematical object and we use this one to generalize scalars, vectors, and also matrices to higher dimensions. Tensors are characterized by their order, like number of dimensions. Sometimes we call them a rank, and the number of the indices required to specify an element. So in machine learning, data science, computer vision, and graph theory, we use them a lot, and we use them for multidimensional data representation, analysis, and transformation. So here you can see one tensor. So you can see it's composed of two matrices, and we show it like Tijk. Tijk. So we show it like D1, D2 up to Dn, and here for D is the size of the ith mode or dimension. So you can see here in I, this I stands for layer or depth. We can say the first dimension, and we select which matrix layer it is. The second one, J, here is the row number or the second dimension. This one is I number 1, and this is I2, right? Then in here, we come for the J. So we can call this I as the layer. And we can go for J for the row number. Row number, it means row number 1 in layer number 1. Row number 2, layer number 1. Row number 1, layer number 2. Row number 2, layer number 2. And this K is for columns. So when we say T11, it means this one, right? 1 is in layer 1, row 1, column 1, right? When we say T112, T112 is this one. So layer number 1, row number 1, column number 2. T221, right? So this one, layer number 2, row number 2, column number 1. And finally, we have this one as layer number 2, row number 2, and column number 2. As I told you, the vector generalizes scalars, vector matrices in the higher orders. So you can see here, a scalar, we call it as rank 0, right? So this is, we call it as 0th order tensor. It's just only one, right? We have a single number, so we can call it as tensor order 0. Then vectors are called as first order tensors or 1D array. So you can see here 5, 9, 1, 3 something, right? Then we have matrices as the second order tensors, or you can say 2D array, right? So you can see here this is a matrix, right? And we have rows and columns. Then we have a rank 3 or third order tensor. You can see here this is one matrix. The next layer is another matrix, right? So we have something like this, right? So if this is the first matrix, then we have another matrix here, right? This is the second one, and we have another one here as the third one, right? So it will be like a cube. We can say third order tensor. We may have fourth order, fifth order. In the case of fourth order, it's a kind of high order structure that we use for encoding relationship along 4 dimensions, right? And for that one, we show like, for example, S, I, J, K, and L. This is for the fourth order, right? And the shape of this one will be M, N, P, and Q. Even we may have fifth order. This is an extension to 5 indices capturing interactions across 5 dimensions. We can show like U, I, J, K, L, M, and the shape will be M, N, P, Q, and R, right? So we may have higher orders, dimensions, tensors as well. Like for vectors and matrices that we did different kind of operations, for the tensors we can do operations as well, right? Tensor operations generalize vector and matrix operations. We include additional operation, we do product, we go unfolding, norms, and etc. So in this lecture we will study them one by one. The first one is summation and subtraction, maybe the easiest one. So if you have two tensors, so this is just, tensor number A and tensor B. So we have tensor A and tensor B. And if we consider new tensor C as the summation of A plus B, then we will calculate the elements of C in this way, right? Simply 1 plus 0 is equal to 1. Element-wise, right? 2 plus 1 is equal to 3. 3 plus 1 is equal to 4. 4 plus 0 is equal to 4. 5 plus 1 equal to 6. 6 plus 0, 6, 7 plus 0, 7, and 8 plus 1 is 9, right? Very easy. Element-wise addition. Then we can do the same thing for subtraction, D. So you can see here 1 minus 0, 1, 2 minus 1, 1, 3 minus 1, 2, 4 minus 0, 0, 5 minus 4, 5 minus 1, 4, 6 minus 0, 6, 7 minus 0, 7, 8 minus 1, 7, right? Element-wise addition and subtraction. This is another example for A plus B. So A We have two tensors b, then again 20 multiplied 19, 39, 21 plus 20, 41, 22 plus 21, 43, 23 plus 22, 45, 20, 47, 25, 24, 49, 26, 25, 51. So we can easily do the summation. Then we go for scalar multiplication. If you have a scalar like s as 2, and we have a tensor here, then for scalar multiplication, if we generate a new tensor and s multiply each element of a, right? So we have 2, right? So 2 multiply a, right? 2 multiply this one, right? So 2 multiply 1 is 2, 2 multiply 2 is 4, 2 multiply 3 is 6, 2 multiply 4 is 8, 2 multiply 5, 10, 2 multiply 6, 12, 2 multiply 7, 14, and 8, 16. Easy, right? Then we go for tensor product, or we call it as outer product. So in here, we combine two tensors to form a higher order tensors. So we may have tensor A and tensor B. So these are the two tensors, and we want to do the product, right? So let's see how we do it. We show this one by A. You can say cross circle B. So what we do here, every element of A multiply whole tensor of B, right? So 1 multiply whole tensor, 2 multiply whole tensor B, 3 multiply whole tensor B, and 4 multiply whole tensor B. So we do scalar multiplication, 1, 0, 0. So this will be the same. This will be 2, this will be 3, and this will be 4, right? So this is our tensor, and we can flatten it, right? So flatten it, it means tensor, we will remove just the sign of tensors, and we will have one 4 by 4 matrix, as you can see here. Then we have tensor contraction. This tensor contraction reduces a tensor order by summing our repeated indices. So you can see here Rij is sum of Tijk multiply Vk. So this equation that we can see here, this shows the process, and this Rij is the resulting contracted tensors, and this Tijk is the original third order tensor, and Vk is a vector that we use in the summation. This helps us to lower the tensor's rank by 1. So let's see here, we have this tensor and this vector. So we want to contract over the third index, right? So R11 is equal to 1 multiply 1, 1 multiply 1, 1 multiply 2, and 1 multiply 3, right? So in here, tensor T has these components, like these two layers we have, and for both set of indices, we have the vector of 1, 2, and 3. So contracting over the third index involves summing the product of Tijk and Vk for each of k. So for R11, we can say 1 multiply 1, 1 multiply 2, 1 multiply 3, and you can do similarly up to Rij6, and this one gives us R as 6, 6, 6, 6. Okay, now it's time to learn about third order tensor operations. We have two tensors. One is A and another one is B. As you can see here, layer number 1, or you can say A1, A2, and A3. This one B1, B2, and B3, right? So we want to do first summation. Summation is very easy, element-wise summation, right? So 1 plus 8, 9, 4 plus 0, 4, 7 plus 0, 7, 4 plus 1, 5, right? 5 plus 2, 7, 9 plus 0, 9, right? Element-wise summation. The same thing for subtraction. 1 minus 8 minus 7, 7 minus 0, 7, 4 minus 1, 3, 1 minus 2 minus 1, 9 minus 0, 9, right? Easily we can do element-wise subtraction. And also we can go for Hadamard product or element-wise product. Simply we can do multiplication, right? 1 multiplies 8, 8, 6 multiply 1, 6, 8 multiply 1, 8, 1 multiply 2, 2, right? 5 multiply 2, 10, 4 multiply 9, 36. This is called as Hadamard product for tensors. In the same way, we can do scalar multiplication. So we have a scalar of 3 and multiply a, right? 3 multiply 1, 3, 3 multiply 6, 18, 3 multiply 8, 24, 3 multiply 5, 15, 3 multiply 9, 27, right? Element-wise, we will multiply 3 into each element of a. Then in here we have third order tensor multiplication. In here we have a different kind of multiplication compared to the previous operators. Each tensor is treated as a stack of matrices along its first axis. So you can see here, we call this one as A1, for example, this one as A2, and this one as A3. So B1, B2, and B3. So we have 3 matrices in each one, right? So to perform the dot product, we call this one as dot product also. So what we do, the first axis must match and the second and third axis of B are transposed to align the inner dimension. So what we do here, first we do transpose, right? So B1 transpose is this one, B2 transpose is this one, and B3 transpose is this one. Then we do multiplication of A1, B1, A2, B2, and A3, B3. So slice number 1 of C as the result of this multiplication. It will be A1 multiplied transpose of B1. So this is the transpose of B1. Okay, first row, first column, this one. First row, second column, this one. First row, third column, this one, right? Second row, first column, second row, second column, second row, third column. And the same we can do, then we will come up this one. So this one will be C1, the first layer of C, right, as the result. Then we do the same for the second slice, A2 multiplied transpose of B2, okay? First row, first column, first row, second column, first row, third column, right? In the same way, we do this multiplication, simple matrix multiplication, and we will come up with C2. Then in the next round, we go for slice 3 or layer 3 for C, A3 multiplied transpose of B3. In the same way, we will do it and we will come up with C3, right? So then we will bring all them together, right? So C1, C2, and C3. So we will come up with this one. This is C1, C2, and C3, right? So we will have the multiplication of A into transpose of B as C1, C2, and C3. And this is the result. The next topic is tensor unfolding. This is also known as tensor matricization. Tensor matricization, or also we call it as flattening. Right? So tensor unfolding or matricization or flattening is the process of rearranging a multi-dimensional tensor into a matrix by unfolding it along a specific mode or axis, you can say, right? So for example, here we call it as mode 1 unfolding. So we have this tensor, mode 1 unfolding. It means just we remove these things and we will have matrix as it's called as tensor 1, right? So we show it as T1 as mode 1 unfolding. The next topic is tensor norm. Tensor norm generalizes the concept of vector and matrix norm that we learned in the previous lectures. In here, we just generalize the matrix norm and vector norm to multi-dimensional array, and this will provide a measure of a tensor size or magnitude. So there are many kind of norms, and Frobenius is one of them. So what we do just, this is the square root of the sum of the squares of all tensor entries, right? For example, this is one tensor, simply root a square of 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7 square, 8 square, then it will give us this one, 14.28 as the norm of these tensor. The next topic is tensor decomposition. This is the process of factorizing a multi-dimensional tensor into simpler and interpretable components. This reduces dimensionality and also computational complexity. There are too many ways to do that, like CP decomposition. This CP decomposition represents a tensor as a sum of rank 1 tensors. Then we have Tucker decomposition. This factorizes a tensor into core tensor multiplied by factor matrices along each mode. Then we have HOSVD. It's a kind of orthogonal version of Tucker decomposition, and it provides mode-wise singular vectors. Later we will study what is singular vector and SVD. Then we have TT or tensor train. This kind of decomposition expresses high order tensor as a square of low order core tensors, and this enables efficient storage and computation. So estimating the appropriate tensor rank is often achieved using iterative algorithms such as ALS, alternating least squares, and this balance approximation accuracy and computational cost. So here we're gonna study CP decomposition. That in this CP decomposition stands for canonical polyadic, and this kind of decomposition, this factorizes a tensor into a sum of rank 1 tensors. So we use this one for providing a simple and interpretable representation of multi-dimensional data. So what do we have here? Tijk is equal to sum of R from 1 to R, AIR1, AJR2, and AKR3. right? So then we have this one T as A1 dot B1 dot C1 A2 dot B2 dot C2, right? So this one is simply the outer product, and the result will be a rank 1 tensor sum to reconstruct the original data. So in here, each element captures a latent factor along each mode. Then we go for symmetric tensors. A symmetric tensor is a kind of multi-dimensional array, and in here, entries remain invariant under any permutation of its indices. So what is permutation? When we have 1, 2, 3, so a combination of 1, 2, and 3, like 2, 1, 3, 3, 2, 1, 1, 3, 2, 2, 3, 1, 3. These all should be the same, right? So in this tensor that you can see here, this tensor is something like this. T is equal to 1, 2, 2, 3, and 2, 3, 3, 4, right? So what we see here as the permutation, T1, 1, 2, T1, 2, 1, and T2, 1, 1, all are the same permutation, right? So this is for this one. So this one is all are equal to 2. So T1, 1, 2, T1, 2, 1, T2, 1, 1, all are 2, right? Then T1, 2, 2, T2, 1, 2, and T2, 2, 1 are 3. T1, 2, 2 is this one, 3. T1, 2, 1, 2 is this one, and T2, 2, 1 is this one. All are 3, right? So you can see that permutations are equal. You can we show like this. Tijk is equal to T pi ijk. Pi ijk is the permutation. It means different combination of this 1, 1, 2 that we have. Okay, that's all for today. Tensors generalize scalars, vectors, and matrices into multi-dimensional arrays. These tensors provide us a unified framework for representing complex data. Core tensor operation we studied, like as addition, scalar multiplication, Hadamard, inner, outer, dot product, we studied all of it. Also, we learned about tensor decomposition, like CP we studied. So these kind of tools are widely applied in machine learning, computer vision, natural language processing, and healthcare. And these enable us advanced modeling, pattern discovery, and computational efficiency in high-dimensional setting. Thank you very much for watching this video lecture. Please feel free to ask me your questions if any. Thank you, and see you in the next lecture.